Thank you for tuning into my presentation. In this talk, I'll be presenting our research on direct written printed coils for resonant wireless power transfer applications. My talk will cover how we fabricate our coils using direct write printing on flexible substrate, and I'll talk about the performance of printed coils and how this could be improved through coil design and through different materials and different geometries. A mandatory introduction is really about why we need resonant power transfer in the first place. What is special about magnetic resonant power transfer? In the figure, we can see the broadband wireless power transfer spectrum all the way from hundreds and tens of kilohertz inductive coupling, which we widely see integrated in consumer electronics, to few megahertz wireless power transfer, resonant magnetic power transfer, which we're looking at in this work, and then we have the radiated power transfer at UHF bands and beyond, all the way up to millimeter wave bands and terahertz, where radiative power transfer gives spatial freedom, but the efficiency is very poor from an end-to-end point of view. Magnetic resonant power transfer is a sweet spot between tightly coupled, high-efficient and safe inductive coupling and the highly ambitious omnidirectional power transfer using radiation and far-field propagation, which is more suited to powering hundreds of remote sensors as opposed to powering a specific device at quite high efficiency. Another mandatory introduction is really about printing and why we need printed coils and why bother printing coils in the first place. I know this is a printed electronics conference, but it might be an introduction I would still need to say. Printing allows rapid prototyping. It allows us to fabricate circuits very quickly. The printer we are using, for example, has a cost of £3,000-4,000, which is over 10 times smaller than the cost of a standard PCB laser prototyping machine. Printing also scales very nicely for high volume applications, and if we have the right low cost materials, it can be much cheaper than photolithography and requires much less initial investment compared to photolithography. And the main advantage of printing is really you can print on anything. Anything could virtually be a substrate. You could print on paper, you could print on fabrics, you can print dielectrics, you can print conductors, and even 3D materials. So we have very high flexibility on why we need to print, why we can print circuits. Now the main disadvantage comes from the materials. Most conductive inks, especially the lower cost ones and the ones more suited to mass productions, have very high resistance compared to solid copper sheets or printed circuit boards, and even compared to lit wires. So we will need to take that into consideration when we design our circuits to overcome the higher DC resistance and obviously high frequency resistance as well. So coming with this idea in mind of highly resistive tracks and highly resistive inks, we need to take that into consideration when we design a coil. The efficiency of the coil is proportional to the conductance. The efficiency of the power transfer needs high quality factor, and quality factor is inversely proportional to the resistance. So we need to design a coil with high inductance, but with also low resistance. So in order to do this, we start by designing a large coil diameter, which is essential to achieve high inductance. We stick to only 2 coil turns because any more number of turns will increase the complexity, will increase the resistance, and will start reducing the quality factor. Now another thing to do with printing is that the resolution will not be as high as circuit boards in many cases, especially with the lower end printing without much optimization. So we need to factor that in our geometry. So our minimum feature is the trace width, which is 1 millimeter to make sure it's more reproducible and more reliable, and the gap between the traces is 4 millimeters. 1 millimeter also being an increased trace width allows us to have lower DC resistance and in the end could increase our quality factor and our power transfer efficiency. The main focus point of this work is the fact that we're doing a double-sided coil design. On the left-hand side you can see a single-sided coil design, on the right-hand side is the same design but for a double-sided coil, and in the middle we have a wire connecting both coils. Now the motivation behind the double-sided coil comes from the additional inductance that we could achieve using a double-sided coil as opposed to single-sided coils. If you consider 2 single-sided coils, which we may think is equivalent for double-sided coils connected in series, then we have 2 resistors and 2 inductors, each coming from a coil connected in series, which simply multiplies the total inductance and resistance by 2. But in reality, when you have a double-sided coil, you're not putting two coils in series. You are putting two coils in series by adding a wire, but you're also adding one more inductor, which is the inductance between the top and bottom sides of your coil. So you do get additional resistance, which is our wire, but the key message in this slide is that we have an additional inductor. This additional inductor could improve our quality factor because it should have larger inductance than the resistance coming in from the wire, which means we can have a higher quality factor, improving our wireless power efficiency. Now, before we move on to our coil parameters and to our performance evaluation, we need to look at the coil fabrication. We use direct wire dispenser printing. The benefit of dispenser printing compared to inkjet printing is that it allows us to realize thick layers of conductive inks quite easily. It also requires much less optimization compared to most inkjet printers, and it's much more straightforward. Compared to screen printing and photolithography, you don't need to buy a screen or a photolithography mask in advance, so it's very well suited for rapid prototyping, where you can just design your circuit, upload it to your printer, and print directly on the circuit, hence the direct write. So it's more like 3D printing, but plainer 3D printing. We use a commercial desktop printer, which is a Volterra V1. That's a very low cost printer compared to large scale screen printers and inkjet printer. It does not require much optimization to get it up and running, so it's very well suited for prototyping again. As we are doing this on a flexible substrate, which is polyimide 75 microns, flexible polyimide that is semi-translucent, we need to adhere the substrate to a rigid surface to keep it planar, and we use alumina tile because of its high temperature resilience for this application. And we start the process by simply jetting our ink onto the substrate. The next step is thermally curing the ink to achieve our smooth conductors, and once the cured silver ink is in place, you just need to clean it and remove it from the alumina surface, and you now have your flexible circuit fabricated. We do the same for the other side of the coil, and we insert a sheet of 100 microns adhesive in between, and we activate it by using a heat press to adhere both sides of the coil together. And the final step is drilling a hole and filling it with conductive epoxy to create a wire connecting the top and bottom side of the coil. Now, looking at the photograph of our fabricated prototypes and from measuring the dimensions of different features, we can see that we have achieved high fabrication accuracy without any tuning or optimization. So this proves that having larger geometry will make your life easier when you are prototyping printed electronics, and in this case it will improve the performance because it means less resistance, more conductivity, and eventually more quality factor. When we fabricated 3 prototypes, we measured very consistent coil parameters with less than 1% variations between the prototypes, so that proves that the fabrication method is scalable and can be used for mass production. Now, how the coils behave when they are bent, how bending affects the conductivity, and if it permanently deforms the traces. This will be something we look at in our future analysis, which is the reliability of the coils and how those printed coils can be made more reliable. And if there is a geometry, they can actually make them more reliable. Looking at our measured coil parameters, we used an impedance analyzer to measure the broadband resistance and inductance of the coil, and then we analytically calculate the quality factor at the frequency we are interested in, which is 6.78 MHz. If we look at the single-sided coil, we can see an inductance of about 0.6 microhenry and a resistance of approximately 4 ohms. For the double-sided coil, we are seeing a significantly higher inductance that's about 4 times higher of 2 microhenries, but the resistance is just over twice that of the single-sided coil. So it really proves the point that the additional series inductors that come in from the double-sided coil structure is more significant than the resistance of the wire, and it can allow us to improve the quality factor. So as we can see, the single-sided coil has a quality factor of 1, but the double-sided coil achieves more than 50% improvement of the quality factor compared to the single-sided coil, fabricating using the same process, fabricating using the exact same geometry. Now, the most important bit, the interesting part, is how does this perform in a wireless power transfer system? How much is the wireless power efficiency? And in order to do this, we could use a signal generator with a voltage and measure it using an oscilloscope. But the most reproducible way and the most And the highest accuracy method is to use a vector network analyzer to measure the same signal and to measure the forward transmission and the S parameters of two coils connected at certain separation from each other. Now we might say that the VNA has 50 ohm ports. In real life our system might not have a 50 ohm characteristic impedance, but when you look at analytical equations for wireless power transfer, magnetic resonant power transfer efficiency, we can clearly say that we could put in a different Z0 or characteristic impedance, and we can predict how the performance will change for a system that has a different characteristic impedance or uses an impedance transformer. We do our experiment at 6.78 MHz, and in order to get our coils to resonate at 6.78 MHz, we get lumped capacitors, standard ceramic capacitors, to match them, and we calculate it using the standard 1/2 pi square root LC relation for the resonant LC circuit. And as we are measuring voltage ratios using the VNA, the power transmission ratio will be the S21, the forward transmission squared. What we're interested in is the efficiency over separation. We vary the distance between both coils for up to 10 centimeters, and we measure both the voltage forward transmission and the wireless power transfer efficiency, which we calculate from the forward transmission. On the left-hand side of the graph, you can see the voltage forward transmission on a logarithmic scale, and on the right-hand side, you can see the power transfer efficiency on a standard linear scale, and we can see that the coil achieves a peak power efficiency of just under 50%. Now, this is not an impressive value, but this is limited by the material properties, it's limited by the conductivity of the ink, and this could be improved by either using higher conductivity inks, or looking at coil geometries, or stacking more layers of the coil to improve the quality factor. Now, a low quality factor is not always bad actually. We found that there is an advantage of having a low quality factor system. A common problem in wireless power transfer and resonant power transfer is frequency splitting. When coils are very close to each other, the mutual inductance becomes higher than the characteristic, or becomes significant compared to the self-inductance of the coil, which results in frequency shifting. So your tuning moves from, let's say, 6.78 MHz to a lower frequency and a higher frequency called the odd and even modes. In this case, because we have a very broadband response, we have a low quality factor, so we can achieve, as you can see in the primary axis as a forward transmission, we can achieve very consistent voltage forward transmission at short distances across a very broadband frequency. So we can see that with a low quality factor coil, we do get the advantage of having a quite broadband response and of mitigating frequency splitting to some extent. Now, I'm not saying we should deliberately design our coils to achieve low efficiency, but it's an interesting conclusion that we can draw, that we should not forget that a low quality factor will imply a more broadband resonant response. So in conclusion, we have demonstrated direct written printed coils with reasonable efficiencies for flexible and wearable wireless power transfer and Internet of Things applications, and we have seen that through the geometry, through the design of the coils, we can improve the efficiency and we can improve the quality factor, which in this case is using a double-sided design, and we have achieved the peak power transfer efficiency with the printed coils of 50%. Our future work will be the bending and reliability test of the wireless power transfer coils. We'll be looking at how the performance behaves with time, how oxidization of the coils happen, and how that affects the efficiency. And we'll also look more into the geometry, into stacking multi-layer coils, and how the trade-off between flexibility, size as well as thickness can improve the quality factor of the coils to achieve the maximum power transfer efficiency. Thank you for listening, and please do send me any questions you might have by email, and do check out the conference paper for more details about our results and the methods, and do email any questions you might have about this work or about the paper. Thank you.